A very good day. I'm Selvin Thread. My matrix number is B0821110041. I'm from 2BEE S102. Here I am engineer from this project. Our task is converter topology buck and input voltage is 18V and then output voltage is 5V. Here's our project abstract, which is designing a control rule for power converter can be difficult, particularly when good performance is required against load and line variations. Then, in order to improve the converter's representation at a high frequency, the study suggests a modeling approach that does away with this presumption. Then the suggested analysis is used with a buck converter. The final outcome will simulated in MATLAB and Simulink environment. Then the introduction. In this study, buck converters, also known as step-down converters, DC to DC converters that increase output current while decreasing input voltage. Components that we are using is MOSFET and IRF521s, resistor, inductors, capacitor, diodes, and DC power sources, which is the components that we are using for our project. The design process is made simpler by reducing the amount of external components in both synchronous and non-synchronous. The project methodology. This project goal is to import knowledge on how power converter control, which depends on DC to DC converter, to calculate the findings, many equations and formulas to verify the results. The project is concluded with a simulation which is made by Simulink and then MATLAB. That's all. Thank you.
So I am the project leader for this project, and I am also in charge of the theoretical calculations for our project. So that being said, let's take a look at the calculations. So for MOSFET 1, there are two equations. So with this, we can find the state space model. So we have di dt dvc over dt. So from that, we can build the matrix form. This is the x dot, this is the ax plus bu. The u is the initial value. So for the output is 0, 1, and this is for the MOSFET off. This is also uses the same concept as the MOSFET on mode 1, and the output is also the same. So for the SSA model, it's also the same concept, but just we will combine the two modes. So the final answer is this from the combination of mode 1 and mode 2. So our company was given 18 volt and the B output is 5 volt. So and we estimate the value for the resistor is 10 ohm and the frequency is 10 kilohertz. So from this we will find the time, which is 0.1 millisecond, and we will also find the duty cycle, which is 27.8%. And we can also find the L min, which is 361 microhenry. From this we will find the inductor, which is 451.25 microhenry. So when our FC is 374.6118 Hz, we can find the LC, which is 1.805 times 10 to the power of -7. And after we find this, we can use the duty cycle, the time, and the LC to find the delta V. For delta V, we just substitute and we will get 0.025, and from this we will find the capacitor. We will substitute all the values, and we got 400 microfarad. So therefore our value for this project is this, and that is all from me. Thank you.
A very good day. Let me briefly introduce myself. My name is Ephraim Simon Rajaram. My matrix number is B0821110057, and I'm from the class 2 BEE section 1 group 2, and I'm be talking about the simulation part of our assignment. As you can see here, this is the circuit that has been used in Multisim. As you can see, it is consists of input, a supply, a MOSFET, a diode, an inductor, a capacitor, and a resistor. And the values for LCR, which is the inductor, capacitor, and resistor, is been done in the calculation part before this. So since we already have our values, we just have to imply it into the circuit and just run it to get the output. As you can see, the inductor is at 451.25 microhenry, the capacitor is at 400 microfarad, and the resistor is 10 ohm. After we have done constructing the circuit, we just connect it to a oscilloscope to get the waveform. Now, if you see the waveform from the beginning until the blue line here, this is when the MOSFET is at on stage. After that, you can see it's a straight line. Until the end, it will be a straight line. That is because it is at off stage. Now, after we have done in Multisim, we also did it in MATLAB. Now, in MATLAB, as you can see here, the RLC here. This RLC here is the same value with the circuit just now. The resistance, the inductance, and the capacitance. As you can see here, same value. Just written it in MATLAB. And then this coding here, in this coding, we don't even have to calculate ourselves. We can just write it like this, and it will calculate it for us. Now, after this, we put the step ABCD so that we can get this graph. Turn on the grid and then put our title. Then we run it. After that, we can get this ABCD. This is the result we get, and this is the graph that it shows from this coding. So this is our simulation part, and that's all from me. Thank you.
Hello, my name is Arvin. My matrix number is B082110310, and I will be explaining the discussion and conclusion for our project assignment. For our discussion for component selection, finding a suitable component for the project specifically for achieving a 5-volt output in the buck converter circuit can be initially challenging. However, the MOSFET IRF520NS diode inductor with the value of 451.2 Henry, a capacitor value of 400 farad, and a resistor of 10 ohms were identified as used as components. For result analysis, the final number obtained is 0.278, which coincides with the value used in the duty cycle calculation as shown in the SSA graph. Various system parameters such as ripple voltage, ripple current, output current voltage, power waveform, and voltage and current in MOSFET, inductors, and diodes are present in the result. Power loss and current conductivity, it shows the impact of ripple voltage and the duty ratio on power losses were studied. Additionally, during the brief duration, the current exhibit a conductivity of 0.6. In the onset, the MOSFET experiences a transient excessive current. For our conclusion, we have understood the basics of the buck converter. Through the study, a comprehensive understanding of DC to DC buck converter is achieved. The buck converter, also known as a step-down converter, reduces voltage from the input to the output while increasing the current load. It achieves this by alternating between the on state and off state. We also learned the continuous mode operation. The buck converter can operate in continuous mode if the current flowing through the inductor never reaches zero throughout the process. This mode ensures a continuous flow of current, enabling a smooth operation of the converter. We also learned designing the cascaded state space controller. For the buck mode of the DC to DC converter, a cascade state space controller is designed using the state space averaging and the pole placement method. State space controllers offer advantages such as flexibility in adjusting the pole position and easy installation by modifying the damping factor and regulation period. MATLAB Simulink is used for final testing of the proposed control structure. Future efforts will be focused on developing controllers for buck boost mode and buck boost mode, as well as comparing the performance of each of the three modes with pi proportional integral regulators. This suggests an ongoing interest in enhancing and evaluating different control strategies for DC to DC converters. So this will be my part, and thank you.